Pluto, a far-off and confounding body, was once viewed as a particular and veritable planet, a member of our planetary family. However, recent upsetting verbalizations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a surprising disclosure. They recommended that this cool world is on a potential crash course with Neptune. But how could this happen? And what might be the outcomes of such a gigantic event? Are we seeing an interesting influenced eccentricity, or is there something else to this coming boundless episode? Join us as we investigate the potential results of a Pluto-Neptune influence. Pluto, a former planet that was consigned to a more humble status, remains a subject of interest and study in the astronomical community. According to steady figures by leading specialists, Pluto's orbit is hazardously near Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are raising the alarm about a potentially dangerous collision between these two planets, which could pose a huge danger to Earth. But how is such an event even conceivable? Pluto's orbit around the Sun is unique compared to any other planet in our solar system. It takes an astounding 248 years to complete a single orbit, which means that since its discovery in 1930, it hasn't even completed one round trip. However, the interest doesn't stop there. Pluto's orbit is characterized by its highly elliptical shape, vastly different from the almost round orbits of the major planets. What makes Pluto's orbit even more striking is its inclination of 17 degrees to the ecliptic plane. The way Pluto follows its orbit is considerably more unpredictable compared to other planets. This inclination and abnormality add layers of complexity to its orbital pattern. Perhaps one of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's orbit. For at least 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, despite what we would expect from their positions in the planetary system. This leads to the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The evaluation of Pluto's orbit began soon after its discovery. Initially, astronomers tried to explain its unusual path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood apart with its dangerous inclination and irregular shape. The mystery surrounding Pluto's orbit can be explained by the three-body problem in celestial mechanics. This is about understanding how three objects in space, like Pluto, Neptune, and the Sun, move and interact with each other through their gravitational forces. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem demonstrates how its orbit, Neptune's orbit, and the Sun's gravity all interact in a complex manner. Terms like asymptotic libration, scope libration, and the VZK wobbling are part of this puzzle. According to astrophysicists, what's keeping all the planets in their orbits is a kind of libration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, its position is always at least 90 degrees away from Neptune. This spatial separation is crucial in keeping their orbits from interfering with each other. Degree libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this suggests that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, adding an extra layer of protection from potential collisions. Another critical factor in this scenario is the VZK wobbling, named after three researchers, VA, LV, and KU, who studied how objects move in space. It's about how three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This pulling affects how they move. In Pluto's case, the VZK wobbling helps us understand why its path near the Sun is so unusual. Despite the apparent randomness, this influence helps keep Pluto's orbit stable for an extraordinarily long time. The VZK wobbling shows that although things in space might seem turbulent and erratic, certain patterns and forces help keep everything under control. These factors protect Pluto's orbit, ensuring it doesn't collide with Neptune or stray off course. This three-body problem affects how we understand these orbits, especially in how space objects pull on each other. Focusing on this helps us study Pluto, our neighboring planetary system, and distant stars and planets. Numerical simulations in the late 1980s revealed that despite these unpredictable properties, Pluto's orbit still remains stable, with small deviations in initial conditions leading to significant differences over long periods. However, these peculiarities of Pluto's orbit have been found to maintain consistency over incredibly long intervals. Later computer models have helped us understand how the giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only factor. Jupiter's gravity also plays a major role in protecting Pluto's orbit, and Saturn helps in that distant region as well. These tests show that Jupiter's gravity alone is powerful enough to ensure Pluto stays on a consistent path for an incredibly long time, perhaps even billions of years. It seems that Neptune, Jupiter, and Saturn are working together to ensure Pluto can continue orbiting safely in space without running into trouble. These anomalies are crucial in the larger context of the universe for maintaining the stability and consistency of celestial bodies. Without these factors, our solar system, as we know it, would be a place of much greater disturbance and instability. Bodies like Pluto could indeed collide with others or be ejected from their stable orbits, triggering a cascading effect on other celestial bodies. For Pluto, particularly with discussions about it possibly colliding with Neptune in the future, understanding its orbit is essential. This gives us a clearer picture of the dynamic nature of neighboring planetary systems. The case of Pluto shows how even in the most seemingly unstable orbits, equilibrium can be achieved through the complex interaction of gravitational forces and orbital mechanics. It also highlights the importance of stability in maintaining the order of our solar system. Perception and investigation of these oddities, to more readily get a handle on our spot in the universe, frequently drives us to face the capricious nature of divine bodies. Furthermore, Pluto's circle is an ideal model of this unconventionality. The possibility of orbital resonance, which suggests the sensitive reliance of a divine body's orbit on its underlying circumstances, is plainly shown in Pluto's case. This implies that even slight changes in the dwarf planet's position or speed can essentially modify its drawn-out orbit. Utilizing programmatic simulations has been crucial for examination to grasp how Pluto moves in space. These models use complex mathematics to reproduce how Pluto, alongside other space objects like Neptune, pull on each other. By changing little subtleties in the simulations, cosmologists can perceive how even minor changes can have a gigantic effect on where Pluto winds up. In the last part of the 1980s, these simulations uncovered something very captivating about Pluto's orbit. Notwithstanding having systems like asymptotic libration and amplitude libration to stabilize it, its orbit can still be ridiculously sporadic. If you start with even a slight contrast in where Pluto is or how quickly it's moving, over numerous years, its path could wind up looking totally different. Regardless of this tumult, Pluto's orbit remains stable for billions of years. This suggests that Pluto's excursion around the Sun has a certain order to it, despite the fact that it appears tempestuous from the get-go. Particularly when it involves whimsical orbits like Pluto's, this presents tremendous challenges. The inherent nature of these systems suggests that long-term forecasts are frequently filled with uncertainties. While mathematical simulations are a fundamental tool for understanding and predicting the future behavior of divine bodies, they also highlight the limitations of our estimates. These models depend heavily on the accuracy of initial conditions and the complexity of the interactions they reproduce. Any slight mistake or deviation can radically change the results, making exact predictions an overwhelming task. Additionally, the violent nature of huge orbits like Pluto's serves as a sign of the ever-changing and dynamic nature of the universe. While we've made gigantic steps in understanding space, Pluto's model helps us to remember how our comprehension of the universe is still limited. Understanding the gravitational impacts of the giant planets on Pluto's orbit offers valuable insights into the broader dynamics of the nearby solar system. It shows how the presence and position of every planet can have sweeping impacts on the stability and trajectory of different bodies within the system. So, why are notable astrophysicists suddenly raising concerns about a potential impact between Pluto and Neptune? Regardless of all of these complex forces attempting to prevent such an event, Neil deGrasse Tyson, a renowned astrophysicist, offers a book-length perspective on the mysteries of our nearby solar system, especially the captivating example of Pluto. Tyson, known for his part in renaming Pluto from a planet to a dwarf planet, gives a quick investigation on the advancing nature of heavenly mechanics and the public's interest in the overlooked corners of space. His position on Pluto's renaming is outlined in the steadily growing knowledge of our solar system. He sees the renaming not as a diminishment but as a vital change in understanding. With our growing comprehension of the many bodies surrounding our Sun, Tyson's approach to heavenly mechanics is one of persistent learning and change. He sees the complexity of Pluto's orbit, as well as its interactions with Neptune, from a perspective that recognizes the unpredictability of space. He suggests that while Pluto's orbit is stable for the present, it could undergo tremendous changes in the future. This possibility serves as a reminder of how much we still need to discover about the forces shaping our planetary system. In the grand scheme of things, Pluto's orbit is an interesting case study in the intricate collaboration of gravitational forces within our nearby solar system. While its orbit is stable right now, the mysterious interactions between Pluto, Neptune, and the other planets suggest that even the most seemingly stable orbits could change over time. As astrophysicists like Neil deGrasse Tyson continue to explore the mysteries of the universe, they help us better understand the delicate equilibrium that governs the movements of divine bodies. The potential for a Pluto-Neptune impact isn't necessarily inevitable, but it serves as a reminder of the continually evolving and perplexing nature of the universe. Regardless of the established theories surrounding Pluto's orbit, it's essential to consider the broader implications of these dynamics for how we understand the nearby solar system and the universe at large. While Pluto's journey is one of curiosity, it is also a reminder that the universe is full of mysteries and complexities waiting to be explored. The concept of orbital resonance, particularly between Pluto and Neptune, is a central piece of the puzzle. This resonance, where the ratio of Pluto and Neptune's orbits is 2:3, is a major part of celestial mechanics. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance ensures that, despite their orbits crossing, the 2 planets never impact. This is a result of the gravitational interactions that stabilize their paths, working together to prevent any catastrophic collisions. The importance of resonance in maintaining stability cannot be overstated. It provides a striking example of how systems in space, even those that initially seem turbulent, can self-regulate through subtle gravitational forces. Understanding this resonance also explains why Pluto, despite its erratic orbit, has remained stable for billions of years. This dynamic is a crucial part of the larger structure of the nearby solar system. The effects of planets like Jupiter, Saturn, and even Uranus are fundamental in maintaining stability in the orbits of smaller bodies like Pluto. Jupiter, with its massive gravitational force, acts as a sort of guardian for the interplanetary system, influencing the orbits of other asteroids and dwarf planets, including Pluto. In fact, some scientists speculate that Jupiter's gravity may have prevented Pluto from being ejected from the solar system altogether. Without Jupiter's protective influence, Pluto's orbit might have been disrupted even further, potentially sending it out of the Sun's gravitational reach.